In this video, we'll discuss how the logical connective not is used in logic and mathematics. So, a logical statement is a declarative sentence that is unambiguously true or false, but not both. So, for example, these statements are all logical statements. They're all unambiguously true or false. 5 is an integer is a logical statement that happens to be true. -5 is not a rational number. That's a false logical statement. 2 less than or equal to 5 is true. 2 cubed is 5. That's false. You might want to compute this one for yourself. Pi to the e is less than e to the pi. That's an unambiguous logical statement that happens to be true. The statement that 11 is even is false. And of course, root 2 is not rational, so the statement that root 2 belongs to the set of rational numbers is false. So these are all examples of statements that are unambiguously either true or false. And so we call them logical statements. In logic, the four main connectives are not, and, or, and implication. In this lecture, we'll discuss the connective not. So let's let P be a logical statement. Then not P is also a logical statement. And then truth value of not P is the opposite of the truth value of P. So we'll denote not P either with tilde P or this kind of sideways L P. Usually we'll use tilde P in this course. And we'll read that as not P. So the truth table for not P shows you what the truth value for not P is given a corresponding truth value for P. So if P is true, then not P is false. And if P is false, then not P is true. The key skill that we want to get across to you is to be able to properly write the negation of a statement. So that's going to be important when you apply negation to mathematical statements and are attempting to prove those statements. So let's look at some examples. So here's a logical statement. 5 is an integer. Now, we could say for not P, we could say, well, not 5 is an integer. But of course, grammatically, it's better to write 5 is not an integer. Okay? 5 is an integer, that's a true statement. So in the negation, 5 is not an integer is a false statement. How about the statement -5 is not a rational number? Well, if we negate that, the negation of that statement is that -5 is a rational number. And of course, -5 is a rational number, so that's the negation of this statement is true. Okay, now we come to the statement 2 less than or equal to 5. The negation would be not 2 less than or equal to 5, which we can better write as 2 is greater than 5 because of trichotomy. If we have a statement like, and of course 2 less than or equal to 5 is true, so 2 greater than 5 is false. If we have a statement like 2 cubed is equal to 5, we can negate that just by crossing out the equal sign. Of course 2 cubed equal 5 is false, so 2 cubed is not equal to 5 is true. We can negate the statement pi to the e is less than e to the pi by just writing pi to the e is greater than or equal to e to the pi. The negation of the statement 11 is even is the statement 11 is not even. And the negation of the statement square root of 2 is an element of the rationals is the statement that square root of 2 is not an element of the rationals. Later, we're going to discuss negating statements which contain the connectives and or, and also negating statements which contain quantifiers. But as a step along the way, you should get used to the idea of negating simple logical statements. Now, we say that two statements are logically equivalent if they always have identical truth values. We want to show an example of that here with not. Let's consider the following truth table. So notice that if P is false, then not P is, if P is true, then not P is false. And then so the negation of not P is going to be true. Not P is true. If P is false, the negation of P is true. And so the negation of P is going to be false. Okay? So notice here that P and the negation of P are logically equivalent. Okay, so P and not P are logically equivalent. We'll see more examples of logical equivalence as we move forward. That's it for this video. Thanks for listening.